Alright, hello everybody, and today we're going to be using complex analysis to solve this integral right here, the integral from 0 to infinity of x to the n minus 2 over x to the n plus 1, where our n right here is some real number greater than 2. So I want to use complex analysis to do this. So first of all, I want to introduce a new complex valued function. So what I'm going to do is I'm going to say, well, let f of z be equal to this integrand right here, but replacing all these x's with z's. So we're pretty much switching from the real numbers over to the complex numbers. So once we have that out of the way, we want to kind of integrate this over some kind of contour somehow. But before we can do that, we need to figure out the poles of this function. So we need to figure out the poles of our function f right now, and how exactly can we do that? Well, poles are just, well, where our function blows up to infinity, and all that happens when our denominator is equal to 0. So pretty much we want to solve for where z to the n plus 1 is equal to 0. And while solving this, you can just, well, first of all bring this positive 1 onto the other side, and then this negative 1 right here, I'm going to rewrite it a little bit, because negative 1, that's exactly negative 1 times 1. But negative 1, since we're kind of working with complex numbers, I'm actually going to rewrite that as e to the I pi. And as for this 1 right here, I'm actually going to rewrite it as e to the 2 pi I times k, where k is some kind of integer. And we want k to go from 0 all the way up to n minus 1. And the reason for doing that is we want to figure out all the possible roots or poles we can have for our function right here. So we have to kind of multiply by this e to the 2 pi I k. Otherwise, without that, we're just going to be solving for one solution. So after n minus 1 repetitions, we're just going to have a repeat of our poles. So we want to stop at n minus 1. All right. So what can we do from here? Well, we have z to the n being equal to this thing right here. So now we want to solve for z. So why not, well, take the nth root on both sides. So now our z becomes, well, nth root of that, just taking the reciprocal of n. So e to the I pi over n. Then over here, we're going to have e to the 2 pi I k over n. Okay, and remember our k is from 0 all the way up to n minus 1. So now let's try and visualize this thing a little bit. Let's see where our roots are. So let's draw up our complex plane right here. So this is our real axis, this is our imaginary axis. And we want to figure out where these points lie on our complex plane. So first of all, why not plug k equals 0 into here. So we're going to have e to the I pi over n, and then this k right here, that's going to turn into 0. So pretty much this whole thing right here just, well, it's just 1. So we're going to have e to the I pi over n. We can say that lies maybe somewhere over here. It really doesn't matter what n is in this case. And actually, just to make things simpler for later, I want to combine these two exponents together. So this will become, we can factor out an I pi over n, and then we're going to have 2k plus 1 on the inside like so. It just makes it a little bit simpler for us. So we have k equals 0. Maybe it's going to be somewhere over here. So e to the I pi over n. And then now plugging k equals 1 into here, we're going to get, well, 2 plus 1, which is 3. So maybe our second point lies over here. So e to the I 3 pi over n. And then you see each time we go up by 1, these numbers in here, these 1, 3, they're just going to go up by our odd numbers. So we're going to have e to the I 1 pi over n, e to the I 3 pi over n, then next we're going to have maybe e to the I 5 pi over n, 7 pi over n, and then so on all the way around. And it doesn't really matter how many we have actually. We actually just want to focus on these first 2 points right here, because we now need to construct for ourselves a little contour somehow that stays consistent for any value of n we have in here. And I think the best, or probably the best contour you can choose is just a little pizza slice kind of. So what do I mean by that? Well, we're gonna go along our real axis here, and then up like that, and then down, so making a little pizza slice. And this contour here, let's call it C, This is the contour that we want to evaluate our function f here over. And then notice it encloses one of our poles right here, so we can use the residue theorem for that. So yeah, let's take a look at this contour in more detail right now. Notice it's going to start from 0, and it's going to run all the way up to, let's say, some big number r. And notice later we're going to be letting our r go to infinity, and this interval right here, this line from 0 to r, this path of our integral, that's going to become kind of like our original interval right here from 0 to infinity. So later we're going to let our r go to infinity, and it's going to match up right here. Okay, so we want to walk this way on our contour, and then after we've reached our point r right here, we want to go upwards along this arch here, and I'm going to call that arch gamma. And then once we reach some point over here, we want to walk down this way again, and then I don't know, let's call that point kappa. Okay, so now we've figured out this path that goes up here, and this is going to be kind of like on a circle. So all the points on our gamma right here will have a modulus of r, so they're going to be a distance of r away from the origin right here. And then the final detail we need to figure out is actually this path right here, because for one, we know that we want to enclose this singular pole right here, but we actually don't know where in between these two poles it should be. So the most consistent way to choose that is, well, just to take the midpoint of these two poles right here. So that point, what it should be is e to the I 2 pi over n, because notice here it's 1 pi over n, 3 pi over n, so here it should be 2 pi over n, like so. So let's actually write down what we have so far. We want to integrate our function f of z over this contour here, this closed contour. So we want to integrate over that contour, f of z dz. And notice that we can kind of decompose this contour into these three paths that we've set up right here. That's pretty much the integral from 0 to r. And then now, first of all, this path right here, that's on the real number line. So in fact, we don't even need to use the z's right here, because we're just integrating on the real numbers. So we can just write f of x dx, then plus the integral over this gamma curve right here of f of z. So because now in the complex plane we have to use the z, and then we're going to add the integral along this kappa right here of f of z dz. Okay, very nice. So now we have this kind of equation right now. Now we can continue on and kind of figure out each of these parts individually. So the first integral I want to focus on is the integral over the contour, because for that integral we can use the Cauchy residue theorem for that, because notice we're kind of enclosing this one pole right here, so it'd be nice if we can use that theorem a little bit. So what does that theorem say? Well, it says this contour integral right here over c, that's exactly 2 pi I times the sum of the residues of our function f of z. So now we have to figure out what our residues are. And notice this is the sum of all the residues, but we only have one pole in here. So pretty much we only need to worry about one residue. So let's actually figure out what that residue at this pole is. So let's calculate the residue at the point z equals e to the I pi over n. So e to the I pi over n of our function f of z. And what exactly is that? Well, we can use the definition of the residue, and that's exactly the limit as z approaches this pole right here, so e to the I pi over n of, well, z minus this pole, so z minus e to the I pi over n, and then we have to multiply it by f of z. And remember, f of z we defined it as z to the n minus 2 over z to the n plus 1. So now we have to evaluate this limit right here. And notice one thing. E to the I pi over n, remember that was the solution to the equation z to the n plus 1 up here. And if we plug this thing into this denominator right here, well, this whole denominator is going to go to 0. And similarly, if you plug e to the I pi over n into this top part right here, that's also going to go to 0. So we have to kind of manipulate this a little bit, maybe use a little bit of L'Hopital's rule. So let's actually clean things up a little bit here before we start doing that. So what I'm going to do is I'm going to distribute this bracket a little bit. So now we're going to have the limit as z approaches e to the I pi over n of, we're now multiplying this into here, we're going to have z to the n minus 1, and then minus e to the I pi over n, z to the n minus 2, over z to the n plus 1. Okay, very nice. Now I can go ahead and use L'Hopital's rule on this one, because now we don't have to deal with this multiplication right here. So using L'Hopital's rule, now we're going to get the limit as z approaches the same pole, e to the I pi over n, of, now taking the derivative of the numerator and the denominator. So the derivative of the numerator, that's going to be, well, dragging the power down, we're going to have n minus 1, z to the n minus 2. Okay, and then we're going to have a minus e to the I pi over n, that's just a constant. Now for this part, we're going to have n minus 2, so drag that power down, then z to the n minus 3. Okay, and all of that junk divided by derivative of the bottom right here, which is just n times z to the n minus 1. Okay, so we've differentiated the top and the bottom, and now we don't have any problems with the zeros appearing on the denominator anymore, because if you plug this into here, we're not going to get a 0. So now, pretty much all we can do is just directly substitute e to the I pi over n into each of these, well, all of these z's right here. So if we do that, what are we going to get? Well, here we're still going to have the n minus 1 like so. Then we're going to have z, but that's going to be replaced with e to the I pi over n. Then because we have a power to a power, we can just multiply the powers directly, so n minus 2 like so. And then minus e to the I pi over n, n minus 2, and then z. That's going to become e to the I pi over n, multiplying this power in, so we're going to have n minus 3 like so. And all of that junk divided by n, then our z becomes e to the I pi over n, multiplying in that power, n minus 1, and we're pretty much done. Now all we have to do is just simplify this a little bit somehow, and then that is our residue finished. So how can we go from here? Well, let's actually start out by expanding these brackets up here and splitting up the exponents. So if we do that, we're going to get n minus 1. Notice I times pi over n times n, that's just I times pi. But e to the I pi, that's exactly negative 1. So first of all, we're going to have negative 1 right here. And then we're still going to have e. Now multiplying by the second part in this bracket right here, we're going to have I times pi times negative 2 over n. So pretty much we're going to have negative 2 I pi over n. So that's this first term dealt with. Now we're going to subtract e to the I pi over n times n minus 2, and then e to the I pi over n multiplied by this n right here. These n's will cancel. We're going to be left with e to the I pi, which is exactly negative 1. Then multiplying by this negative 3 in the exponent right here, e to the I times negative 3 times pi divided by n. That's going to be e to the negative 3i pi over n. Okay, so that's the numerator dealt with. Now we're going to divide everything through by whatever the denominator evaluates to. So we're going to still have the n right here. Then same deal right here. And then n will cancel out. So we're just going to have a negative 1 because that's e to the I pi. And then we have negative 1 right here. Multiplying that in, we're going to get e to the negative I pi over n. Okay, very nice. Now all we need to do is simplify things a little bit, because notice negative 1, negative 1, negative 1, all those can just cancel out. And then now we just have to simplify our exponentials a little bit, because notice in this term right here, e to the I pi over n, e to the negative 3 pi over n. That can actually simplify to e to the negative 2i pi over n. So I'm just going to erase this last part right here, and then we're going to have negative 2i in the exponent like so. And notice one cool thing right here, these two parts right here look the same, so we can factor them out a little bit. So now we're going to have e to the negative 2i pi over n, and in the inside we're just factoring, so we're going to have n minus 1 minus n minus 2. Okay, and everything's still divided by n times e to the negative I pi over n. Okay, right in here, n minus n, that's exactly 0, so those cancel out. Negative 1, negative, negative are positive, so negative 1 plus 2, that's 1. So all of that turns into 1. So we can forget about that junk right there. And then now all we need to worry about is this last exponent right here. We can bring that up to the front by flipping the negative sign in there. So e to the I pi over n. And multiplying these two together, well, negative 2 plus 1, that's exactly negative 1. So now we're going to have e to the negative I pi over n divided by n. Alright, so this is the residue of our function at the point e to the I pi over n. So now, to finish things off right here, we need to multiply that by this 2 pi I to get the final value for our contour integral. So in the end, our contour integral over c, that's exactly 2 pi I times this residue right here. So e to the negative I pi over n, or divided by n. And we can just clean things up a little bit, that really doesn't matter. 2 pi I e to the negative I pi over n, or divided by n. So with that out of the way, we can go ahead and figure out our other integrals. Alright, so I've written down the result for our contour integral, and the next integral I'd like to evaluate is our integral from 0 to r actually, because this is going to be quite easy. So our integral from 0 to r of f of x dx, well, that's exactly the integral from 0 to r. Now f of x, remember by the definition of our function up here, it's z to the n minus 2 over z to the n plus 1. So if we have x's in our function, it's just going to be x to the n minus 2 over x to the n plus 1 dx. And then now what I'm going to do is I'm going to let this r approach infinity. So if we take the limit as r approaches infinity of this integral from 0 to r of x to the n minus 2 over x to the n plus 1 dx, that's going to turn into our original integral we had at the very start. So the integral from 0 to infinity of x to the n minus 2 over x to the n plus 1. And I'm actually going to call this integral I right here. So let's just, might as well do it now, call our original integral we had at the very start I. So if we take the limit as our r approaches infinity of our integral from 0 to r right here, it's just going to turn into our I. So this integral, in the limit as our r approaches infinity, it's just going to turn into I. So actually this whole line I'm going to write underneath right here, that's going to be what happens in the limit as our r approaches infinity. And with regards to our contour integral right here, the value of this integral actually won't change even if we let our r approach infinity, because it's still going to be enclosing the exact same pole. And the residue theorem is not dependent on what contour we take. So the value will still be the same. So with that out of the way, the next integral I'm going to evaluate, let's actually take the integral over gamma right here. So let's take the integral over gamma of f of z dz. What I actually want to do with this integral right here, since we're going over this arc right here, you can kind of think about it as using Jordan's lemma, but I'm going to evaluate it in a more formal way and show that this integral still indeed does go to 0. So to show that this integral goes to 0, we first actually have to estimate this integral. So to do that, let's just put absolute values around it. And well, now we can just plug the definition of our f of z in. So this is the absolute value of the integral over gamma of z to the n minus 2 over z to the n plus 1 dz. And then now what can we do with this right here? Well, we have a path over gamma. So why not try to introduce a new parameterization for this path gamma right here? So I think the best way to do this is just to introduce a new substitution, because the gamma, that's just along a kind of circular path right here. So what I'm going to do is I'm going to let our z's right here be equal to r times e to the I t, where our t runs from 0 to 2 pi over n. And why exactly 2 pi over n? Well, remember in our contour we drew up before, this line right here, we only wanted to walk along our gamma up to a certain point right here. And this point lies on a line that passes through e to the I 2 pi over n. So 2 pi over n is in fact the angle right here. So 2 pi over n in radians. So if you look at our parametrization right here, we have r times e to the it. So that's pretty much a circle of radius r around the origin. And then our t, that's just the angle. So we want to start from an angle of 0 and go all the way up to an angle of 2 pi over n. So that's why this parametrization works for this path right here. So now after we've done that, what we can do is differentiate both sides. So we have dz being equal to I times r e to the it dt. Now, using all this stuff right here, we can substitute it into our integral. So this is the integral from 0 to 2 pi over n. So instead of our gamma right here, we're going from 0 to 2 pi over n right now of z. And z is exactly r e to the it to the n minus 2. And then we have r e to the it to the n plus 1. And then dz, that becomes I, r e to the it, dt. Okay, absolute values around that. And we can just simplify things a little bit right here. That's exactly the integral from 0 to 2 pi over n. And we can kind of distribute this power into these terms right here. So we're going to have r to the n minus 2, e to the it, n minus 2, then over r to the n, e to the I, t times n, and then plus 1. And then we're going to have, let's bring these constants here out to the front. So we're going to have I times r of e to the it. Okay, and what can we do from here? Well, we can use the integral inequality to kind of bring this absolute value inside of our integral. But before we do that, let's actually split the absolute values up right here, because we have this I times r right here. And notice absolute value of I times r, that's just going to be r. We're assuming r is some positive number. So we have r times the absolute value of our integral, and using that inequality I said before, that's going to be less than or equal to r times the integral from 0 to 2 pi over n of the absolute value of r to the n minus 2, e to the it, n minus 2, over r to the n, e to the I, t times n, plus 1. And then we can kind of split the absolute values up right here because we have a multiplication. But the absolute value of e to the it, that's just 1 because we're on a unit circle. So let's just forget about that. Then enter absolute value, and then we have a dt. All right, where can we go from now? Notice that we have something divided by something, so we can kind of split the absolute values up like so. And then here we also have multiplication, so splitting the absolute value up further. Absolute value of r to the n minus 2, that's just going to be, well, just r to the n minus 2 itself. And then absolute value of this e to the I something right here. E to the I, t to the n minus 2, that's some real number. And whenever you have e to the I times some real number, the absolute value of that, that's just going to be 1, because like before, we're on the unit circle. So this evaluates to 1. And on the denominator right here, we'll deal with that later. So let's just write this out. This is going to be r to the n minus 1 now. So we're bringing this r to the n minus 2 out to the front. So we're going to have r to the n minus 1 integral from 0 to 2 pi over n. And then we're going to have 1 over r to the n, e to the I, t times n, plus 1, absolute value of that, dt. Alright, so from here, how can we kind of further estimate this integral right here? Well, we have to take a look at the denominator, because we have the absolute value of something plus something. And whenever you want to estimate something like that, we want to use the reverse triangle inequality. So what does the reverse triangle inequality says? It says that if you have the absolute value of a minus b, that's going to be greater than or equal to the absolute value of the absolute value of A minus the absolute value of B. So how can we identify our A's and our B's in this case? Well, you see we have a positive 1 right here, but we want a negative. So what we can do is we just subtract off a negative 1 instead. So now our A becomes this term right here, and our B becomes just negative 1. So if you can kind of extract that part right there, we have the absolute value of r to the n, e to the I, t times n, minus negative 1. Using the reverse triangle inequality, that's going to be greater than or equal to the absolute value of this thing right here. So absolute value of r to the n, e to the I, t times n. And then minus the absolute value of -1, but the absolute value of -1, that's just 1. So I'm just writing it like that. Okay, and here we have a multiplication. So let's actually split that up a little bit. And then just like before, absolute value of e to the I times some real number, that's just going to be exactly 1. And notice absolute value of r to the n, that's just r to the n itself because it's some positive number already. So now we're going to end up with r to the n minus 1, but inside of an absolute value. But the thing is, later, r will be a really big number. So as long as r is a really big number, this -1 won't do anything to it to make it a negative number. So we can actually get rid of these absolute values right here. So what exactly did we find out? We found that this denominator right here, or this one rather, that's greater than or equal to this value right here. But notice we have 1 over something. And whenever you have 1 over something, that's going to be less than or equal to 1 over whatever the result is. So what exactly does this mean? It means that this whole entire integrand right here, that's going to be less than or equal to this thing right here. And since we're integrating something that's less than or equal to something else, the value of the integral will logically be less than or equal to the original integral. So this thing is less than or equal to r to the n minus 1, integral from 0 to 2 pi over n of 1 over r to the n minus 1 dt. And this whole thing right here, that's just a constant, so let's actually pull that out to the front. So this thing will end up being equal to r to the n minus 1 over r to the n plus 1 integral from 0 to 2 pi over n dt. And it really doesn't matter what happens with this integral right here, it's just going to be some real number. So let's actually replace this integral with some kind of constant. It really doesn't matter what constant we choose, let's just call it c. And you see, remember before we wanted to let our r approach infinity. So letting our r approach infinity, this whole thing right here will actually go to 0, and you can kind of see that for yourself, because we have an r to the n right here, which will grow much faster than this r to the n minus 1. So that means the denominator will outgrow the numerator, and we're going to get a 0 in the limit as our r approaches infinity. So pretty much the integral over our gamma in the limit as our r approaches infinity, that's going to be equal to 0. So now we can kind of add that to our final expression. This integral over gamma right here, that's going to contribute absolutely nothing to our contour in the limit as our r approaches infinity. Alright, so the final integral to evaluate is the integral over kappa. So the integral over kappa of f of z dz. How exactly can we go about doing that? Well, let's just first of all plug in the definition of our function. So we have our kappa, and then we have z to the n minus 2 over z to the n plus 1 dz. And now what can we do with this right here? Well, we need to parameterize this integral a little bit somehow. So we can have some kinds of real interval right here instead of some complex curve in the complex plane. So how exactly can we do that? Well, notice for our kappa, we're walking along this line right here. So we're walking along that path. So how can we parameterize our integral to be on this path right here? Well, if you just consider e to the I 2 pi over n, which is one of the points that this path passes over, then if you multiply it by some scalar, I don't know, let's just call it j, then that's going to move that point on here backwards and forwards along that line right there. But the thing is, it's still going to make the same angle 2 pi over n with the positive real axis. So if we can find some kinds of j that we can use, that kind of starts right here and goes all the way down to 0. That's going to be our parameterization. So we know that we want to start at the point r e to the I 2 pi over n, which is all the way up here, and we want to walk down towards 0. So if we maybe say r minus t, where our t goes from 0 to r, notice that this actually works, because if we start at t equals 0, then that's just going to be 0, and then we're going to have r times e to the I 2 pi over n, which is all the way up here. And then as we let our t go towards r, we're going to have r minus r, which is 0. So we're going to start here, and then we're going to go along this path and end up at 0. So this parameterization works right here. So let z be equal to this new thing right here, and t goes from 0 to r, and now we can differentiate both sides. So dz, that's going to be equal to, well, the derivative of this thing, which should turn out to be, well, we have a negative t in here, so we're going to have a negative. This thing's just a constant, so negative e to the I 2 pi over n dt. And now what we can do is substitute all of that information into our integral. So this is going to be the integral from 0 to r of, well, we're going to replace z with this whole junk right here. So that's going to turn out to be r minus t to the n minus 2, then multiplied by this thing right here, so e to the I 2 pi over n, multiplied by n minus 2, and all of that junk divided by r minus t to the nth power, e to the I 2 pi over n to the nth power, plus 1. And then our dz becomes negative e to the I pi over n dt. And notice one nice thing right here, we have e to the I pi over n to the power of n. These two n's right here actually cancel out. And e to the I 2 pi, that's exactly 2 pi I. And notice 2 pi, that's exactly a full revolution. So in fact, e to the 2 pi I, that's going to evaluate to 1. So that's going to disappear. And now what can we do from here? Notice that we have this term right here and this term right here. That is just constant, so independent of t. So why not chuck all of that junk out to the front? We're going to get, let's actually expand out this bracket right here while we're at it. So I 2 pi over n times n, that's exactly I times 2 pi. But e to the I times 2 pi, that's exactly 1. So we can forget about this first n right here. And then we have a negative 2. If you multiply that into here, we're going to get e to the negative 4 pi over n. And then multiplied by this thing right here, we're going to have a negative in front right here. E to the I 2 pi over n. And if you simplify this, 2 pi minus 4 pi, that's exactly negative 2 pi. So this whole thing right here, we can rewrite it as negative e to the minus 2 pi I over n. And then now we have the integral from 0 to r of r minus t to the n minus 2 over r minus t to the n plus 1 dt. Alright, and you see, now we have this integral right here, and then we have an r minus t right here and an r minus t right here. So that's a pretty obvious thing as to what to do. We can actually just use a substitution right now. So now if we let, I don't know, let's take some new variable u be equal to r minus t. Well, that means du is equal to negative dt. We can kind of rewrite this integral a little bit. So now we have negative e to the negative 2 pi I over n. And then now we have the integral, and plugging 0 into here, we're going to get r minus 0, which is r. Plugging r into here, we're going to have r minus r, which is 0. And then r minus t, that's exactly u. So u to the n minus 2 over u to the n plus 1 dt, that's going to become negative du. And in fact, we can use this negative right here to reverse the orientation of the integral. So we have the integral from 0 to r of this thing times du. And notice this thing right here, that looks a little bit familiar because u is just a dummy variable. We can literally have any variable we want. We can have a banana in here instead of u, we can have a dog or whatever. It's just a dummy variable. So why not replace our u's right here with just x's instead? Because in doing so, that is pretty much the exact same thing as our original integral we have, but except instead of r, we need infinity. So we might as well take the limit as our r approaches infinity now. So taking the limit as our r approaches infinity, we're going to have, well, first of all, we have negative e to the minus 2 pi I over n, integral from 0 to infinity of x to the n minus 2 over x to the n plus 1 dx. And that's conveniently equal to this constant right here, negative e to negative 2 pi I over n times I. So this thing right here is the value of our integral over kappa. So let's write that into our final expression. Alright, so we have the final piece of our puzzle right here. And now what we have to do is just put everything together and solve for what our I is equal to. Alright, so putting everything together right now. We've taken the limit as our approach is infinity on all of these parts right here, and these are the final results. So now all we really have to do, this shouldn't be a negative right here. So we have negative. All we really have to do now is solve for our I, because our I is the original integral we wanted to evaluate. So first of all, let's us kind of factor things out a little bit here. So we have 2 pi I times e to the minus I pi over n. Well, this 0 we can just forget about. We have 2 i's right here, so let's factor that out. So we have I. 1 minus e to the negative 2 pi I over n. And now what can we do from here? Well, we have this exponential right here. What I'm actually going to do is I'm actually going to bring this onto the other side. So we're going to multiply both sides by e to the positive I pi over n, which will cancel out with this part right here. And then here, I'm going to use this thing right here and distribute it into this bracket. So now we have 2 pi I over n being equal to I. And then now we're going to have e to the I pi over n minus, and then negative 2 plus 1, that's exactly negative 1. So e to the minus I pi over n. And you may notice why I did that, because this almost looks like the complex definition of this sign evaluated at pi over n. So let's actually continue with this. So what we're really missing down here is a 2i, and we can actually grab that 2i from right here. So if we bring that onto the other side, we're going to end up with pi over n being equal to I times e to the I pi over n minus e to the minus I pi over n, all divided by this 2i right here. And this right here, that's the complex exponential sign. So now we have pi over n being equal to I times the sign, and the argument will actually be this pi over n right here. So the sign of pi over n, and we are very close to being done. Now we have to divide both sides by sine of pi over n, and we end up with a final expression. I is equal to pi over n over the sine of pi over n. So this is the final result we end up with after all of that work. So in the end, after all of that work, we found out our final result, that the integral from 0 to infinity of x to the n minus 2 over x to the n plus 1, that's exactly pi over n over the sine of pi over n. So a really nice thing about this result right here, if you've watched Dr. Payam's video on the integral from 0 to infinity of 1 over x to the n plus 1, you'll know that it's going to give the exact same result, which is pi over n over sine of pi over n. And that's the value of this integral right here. So what we found out today is that this integral right here, its value is the exact same as this integral right here. So that's a really interesting relationship between these two integrals. If you have x to the n minus 2 up here, it actually doesn't change the result of the integral, which is really quite interesting. So yeah, that's pretty much all for this video. I hope you guys enjoyed this considerably longer video, but yeah. Until next time, have a wonderful day, and bye-bye.